All right. So we'll set this up. You guys said you wanted A as 0, right? So we'll start with A as 0, and we'll modify from there. So the first thing that I'm going to do is make some measurements on my ball as it falls. Whatever you're doing measurements with an object that's falling, it's really important to always measure it to the same place on the object. So you don't want to measure it from the bottom of the ball in A to the top of the ball in B, because that actually cheats you out of a little bit of distance. For things like this, I like to do the edges of the object, so either the top or the bottom, because it's easier than trying to judge where the center is. And that is where you can introduce some error. So the first thing I'm going to record here is the difference in distance between these points. So if I decide that point, the bottom of A, is my 0 line, right? This is 0 meters. It's meters because our scale is 1 centimeter equals 1 meter. So every centimeter that we measure, we really should be recording as a distance of meters. Okay. So that's not super critical error. It might mean that your calculations have centimeters instead of meters if you didn't convert that. But I'm going to measure this. I'm going to scooch my stuff around here because I like to look at it from above so that I make fewer mistakes. And when I measure it from the bottom of the ball to the bottom of the next ball, I get a distance of 3.5 centimeters, which means it's going to be 3.5 meters. But I've measured downward, right? So should this be positive or negative? It should be negative, right? So we're going down. Oh. No. Just don't freak out. Don't freak out yet. Nobody freak out. I'm just going to make some measurements, and then when we do the calculations, you can see if your calculations got you to the right answer. Because there's a couple of different ways you can do this and get it right. Just hang on. And if I measure all the way down to the next one, here I'm at minus 8 meters. Next, I'm going to measure down to the bottom of D, and that's minus 13.5 meters. And then the bottom of E is going to get me to negative 20.0 meters. Now, another way that you could look at patterns here is you could look at the differences between these. So I don't like to put green next to that. So the difference here would be 3.5 meters, right? And it's minus 3.5 meters. The measurement between the next two should be 4.5 meters. Between the next two, do you guys see a pattern here? The next two is minus 5.5 meters and then minus 6.5 meters. So if I'm looking at the change in position, I can see a pattern there. Patterns are good. We're looking for patterns in physics. So we know that. We also know that each one of these represents 1 second of time. So this is 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. All right, so there's some data that we can work with about this object. You guys have any questions so far? Nobody's freaking out yet, right? No. Okay. No freaking out yet. All right, so I'm going to flip back over here. My first question says, what's the average velocity of the ball between points A and E? If I'm going to calculate average velocity, I remember from a couple units ago that my average velocity is going to be the change in displacement divided by the change in time. Dr. Malley's just going to write this out the long way. So my position at E minus my position at A divided by the change in time between them. So the change in time here from A down to E is going to be 4 seconds. I already know that part. My position at E, minus 20 meters. So I'm going to put minus 20 meters and then minus whatever A is, which is 0 meters, right? That's that position. Another way that you could do this is to look at the differences between each of these dots and add them up. Did anybody do it that way? That's one way people like to do it. Another way you can do it is just measure the difference between those two with your ruler. That's another way you can do it and be okay. So I have here that this is going to be minus 20 meters divided by 4 seconds, which gives me minus 5 meters per second. Another way that you could have written this answer is 5 meters per second and then tell me downward, because that tells me what direction. The sign tells me the direction, or you can just tell me the direction. How'd you guys do on that one? Yeah. See, there's more than one way to do it. So that's something that I look out for if I give you something like this on a quiz or a test. As long as you're being internally consistent, that's going to be okay. So you could even decide when you're doing your problem, I want to make this 0, but I'm going to make this direction positive because I don't want to deal with negative signs. And you could do that as long as you told me that positive was the downward direction. All right, next it says, what's the average velocity of the ball between A and C? We're going to do the same kind of thing. Change in position over change in time. Only this time our position is going to be C minus A. The time between those two, I don't even like to bother writing the time part out of this. A and C is going to be 1, 2 seconds. My position at C is minus 8. And then I'm going to subtract from that 0. That's easy. 2 seconds. And we can do this in our heads. Is it okay if I do this one in my head? Minus 8 divided by 2, minus 4 meters per second, or you might have said 4 meters per second downward. The next question says, what's the instantaneous velocity of the ball at point B? All you need to know to be able to figure this out is that the instantaneous velocity at B is equal to the average velocity between A and C. And we already calculated that. The average velocity between A and C was our answer to number 2. And it's minus 4 meters per second, or 4 meters per second downward. How are you guys doing on recognizing average velocity and how it relates to instantaneous velocities? Is that part making sense? Cool. Number 4, what's the average velocity between C and E? So we're going to do average velocity between C and E. All right. Our position at E minus our position at C divided by our change in time between them. Our position at E is minus 20. Our position at C is minus 8. The time between them is 1, 2 seconds. So this is going to be 12 meters, minus 12 meters, divided by 2 seconds, 6 meters per second. I forgot the negative. What do you guys notice about our velocities here? They are all negative. Did you say, whoa? Check this out too. We know our instantaneous velocity at B is minus 4 meters per second. We know that if our average velocity between C and E, that our average velocity between C and E is going to be the instantaneous velocity at their midpoint. So that's going to be this guy right here. Write that down there. Do we know, have we already calculated what the instantaneous velocity at C is? Did we calculate the average velocity between B and D or A and E? We did A and E in number 1. So this minus 5 meters per second is right here. Do you guys see a pattern there with our velocity? We could make a prediction. Remember, acceleration is how much your velocity changes each second. How much does our velocity change each second here? It changes by 1, right? It's changes by -1. So could we make a prediction about what it would be at E? What do you think? I think you're probably right. I think it probably is -7. And what about at A? -3? Or 3 meters per second downward. All right, so it says how much time has elapsed between the time that the ball was at B and the time that the ball was at D. This seems like really straightforward, right, guys? So my time at D minus my time at B, and that's going to be 4 seconds minus 2 seconds, I think. Oh, no, it's 3 minus 1, isn't it? B is after 1 second, right? Because if A is 0, B is 1, D is 3. So that's how I charted mine. If you made this 1 second and this 2 seconds and this 3 seconds, then it might be different. Sorry, this should be 3 and this one should be 1. So it's going to give me 2 seconds of difference. And then it asks, what's our acceleration? You guys already made a prediction about that. If we look at the pattern, our pattern indicates that it's minus 1 meters per second per second. So that's going to be minus 1 meter per second squared. If we want to do that algebraically, our acceleration is going to be our change in velocity divided by our change in time. And we figured out a couple velocities. The ones that I want to use are D and B, right? Because we calculated those specifically for instantaneous velocity. So if we do our velocity at D minus our velocity at D and divide it by the amount of time between them, which is 2 seconds, D is, yeah. So D is minus 6, B is minus 4. So we're going to do minus 6 meters per second minus 4 meters per second divided by 2 seconds. So minus 6 plus 4 gives me minus 2 divided by 2 seconds. Check it out, guys. Minus 1 meter per second squared. So we were right. This last question. How high above point A was the ball released? There's 2 ways we can solve this. How did you guys solve it?
I did that, it was like finding the displacement in the last worksheet where it's like the quantity of velocity 1 plus velocity 2 divided by 2 times the time.
Yeah, that'll get you there. So here's the way that I like to do it for this problem, because what this is really asking us, the thing that you have to realize is that when the ball is released, what's our velocity when something gets released? Does an object start with velocity? No. So this is asking us when or where, because it's asking how high, right? So that's really where. But when or where was was the velocity 0 meters per second? That's really what we're trying to figure out. If I look over here at my chart, come on, video. If I look at my chart, I've got a pattern, right? Do you see? Here's my velocity. Can I back this up until I get to 0? We can make minus 2 meters per second, minus 1 meters per second, minus 0 meters per second. Right? Do you guys see that? So that looks like I've got to make 3 dots. And that would tell me when. How can I figure out how high it was at that point? What pattern can I use? The which one? Yeah, there's a pattern here where I have minus 3.5, minus 4.5, minus 5.5, minus 6.5. So if I go up 2.5 in that gap, 1.5, and then 0.5, does that get me up to where my dot originated, where my ball was dropped from? What do I get if I add all these together? 4.5. Yeah, we think that this is 4.5. Do you think it's right? Is that what you got right? Look at you guys. And you guys were all nervous about this. How much time did it take? So here's another second. I'm like going backwards in time, so I'm going to make it negative because why not? We can time travel, right? Minus 2 seconds, minus 3 seconds. So 3 seconds back and 4.5 meters. How'd you guys do? Did you get that? Sorry. Did you guys do it algebraically or by looking at the chart? Do you like the chart way? So guys, this is why being able to think about things graphically is important. I could have made this on a graph and then charted it out and figured it out that way too. Sam.
For 7, why do you do B, B, and D?
What?
Why do you use
Why did I use those two?
Yeah.
Because those are the ones that we calculated over here. So we calculated calculated instantaneous velocity at B and instantaneous velocity at D.
So you can just do any 2 points.
Any 2 points. You could have, if you realized that this was B, right? You could have used that one and this one, and you would have realized, okay, this is for point C and this is for B. They're 1 second apart and -1 meter per second apart. So you could have used any 2 dots. It does not matter. What was that?
I don't know what I did, but it was not that.
Okay, what ways did you guys figure this out algebraically? What did you do, Natalie?
It was that it was like the quantity of velocity 1 plus velocity 2 divided by 2 and then multiplied by the time.
Yeah, so how'd you figure out what time to put in there? Didn't know about the 3. Okay, so to get to the 3, hold on, I did it earlier. I'm just gonna make sure I do it efficiently. You what?
I really don't remember how I did it.
No, it's okay. All right, so this does work. Here's how you have to get there. In order to solve for time, what you have to recognize is that your acceleration is your change in velocity divided by your change in time. And what you're trying to do is go from an initial position of an unknown height to A. So those are your 2 points that you're looking at. So what you've got to do is set this up so that you've got your final velocity, which is the same as your velocity at A, right? So I'm just gonna make that A, minus your unknown velocity, or your velocity at the initial position. I'm not sure what to give that. Should we give it a question mark or like an I? Let's give it an I for initial. Do you guys not like this method? So there's our initial position. We know that our velocity at our A position, you guys remember? My A position, I assigned a time. I assigned it a time of 0. So we have to figure out how far in the past we have to go. So this has a time of 0 seconds, and I'm going to subtract from that whatever my time is at my initial position. And this is the thing that I'm going to solve for, my initial position time. Actually, I'm going to change this up to be a little more consistent here. This is our time at A. All right. So we've got 2 pieces here that coincide with our A point, and our 2 pieces of information that go with the initial point that we don't know where or when it is. So we do know this information, right? Our velocity at A, we figured this out. Our velocity at A was -3 meters per second. What's our initial velocity going to be? 0. So we got -3 meters per second minus 0 meters per second. We know that our A time is 0 seconds, and our initial time is what we're trying to solve for. What is our acceleration equal to? Yeah, so we're going to set this up all equal to -1 meters per second squared. And so then this is the equation that we're going to work with.
Isn't it 1 velocity second?
1 velocity seconds? Yes. But the units for velocity are meters per second. So it's meters per second per second. Yes. All right, so I'm going to solve this. I've got -3 minus 0, so I've got -3 meters per second. And then down here on the bottom, I just have minus my initial time equals -1 meter per second squared. Now, guys, if something is equal to 1, what does that mean the denominator has to be equal to? No. If our numerator is 3, it's got to be the same, right? So we know that the value here for t has to be 3 seconds. So we have to go 3 seconds sort of backwards in time, right? Is that what happened? 3 seconds backward, -3. So that's what we thought graphically was happening. So if it's 3 seconds backward, it's -3. Because when we rearrange the stuff, if we switch these spots, right, it's going to be -3 divided by -1 equals minus ti. And they all cancel each other out. Okay, so then what do we do about this guy right here? We're back to our two velocities problem, right? So if our position is equal to our velocity at A plus our velocity at the initial position divided by 2 times the time, we know that the velocity at A is minus 3 meters per second. Our initial velocity is 0 meters per second divided by 2. Times our, remember we're going backwards in time, our minus 3 seconds. All right, what's minus 3 divided by 2? So we got minus 1.5 meters per second times minus 3 seconds gives us 4.5 meters. And this number is positive, right?
Is that all just answer number 8?
Yes. This is the math way to do it.
So you could just go 2.5, 1.5, 0.5, and that's it.
Yeah, as long as you tell me what you did.
Or we could.
Yeah. So if you want to solve a problem with a really good quantitative picture, you can do that. If you want to solve a picture with a graph, you could do this graphically, right? You could plot all of the stuff by time. You could do that. If you want to solve it algebraically, you could do that. Any of those is okay. How'd you guys do on this? You all sound a little bit horrified when I started like marking up my paper. But you feel better about it now. Yeah, you guys did great. So in physics class, there are usually different ways that you can solve a problem, and that's okay with me, as long as I can see what you were doing and it made sense. Is that okay with you guys? Yeah. So that's why I ask you guys to show your work, because as long as your problem is being internally consistent, even if you make mistakes, a lot of times students don't make big mistakes. It'll be something like they used the wrong sign, or they put the wrong variable someplace, or they made an algebraic mistake. And I want to give you guys as many points as you can for showing what you do know. My goal isn't to trick you into messing up somehow. Do you guys have any questions for me about these? No questions? Okay, that's what I planned for today. So great job, everyone.